Yes, madam.
Yes, please you start.
Yeah, I'll carry on for here. Am I audible?
Yes.
Okay, thank you, madam. Good afternoon, participants. We have reached to the fourth session of the second day, and topic is handling infrared image processing. And for this session, to engineering, Dehradun. Sir, on behalf of the organizing committee and on behalf of the participants, I welcome you both to this session. Before the session starts, I would like to give a short introduction about our research persons. Dr. Muthu Kumar is a distinguished researcher who had dedicated his career to advancing the field of machine learning and deep learning. His research efforts are primarily focused on leveraging these technologies to identify and predict diseases and develop effective health monitoring solutions. One of his significant contribution to this field is groundbreaking method for monitoring and activity using advanced deep learning and computer vision techniques. He has an impressive background in machine learning engineering, having previously worked as a computer vision engineer at Motif Research Co. in Tokyo. His and deep learning have been widely recognized in his presentations delivered at numerous international conferences. His work has had a significant impact on the healthcare industry, and his innovative solutions are helping to transform how we approach disease identification and health monitoring. His unwavering commitment to advancing the field of machine learning and deep learning has made him a valuable research community, and his continued research are sure to drive further innovation in this exciting field. With this, I welcome Dr. Muthu Kumar to this session. In this session, along with Dr. Muthu Kumar, we have another research person, Dr. Kumar Dron Shrivastav. I'm reading out a brief introduction about him. He's an experienced researcher in public health informatics with demonstrated knowledge of information technology and public health in India and abroad. Skilled in R, SPSS, PHP, RDBMS, Java, HTML, and requirement analysis, and other AI-enabled software development tools and techniques. Strong communication, networking, and skills for better management, monitoring, and evolution of resource. For instance, in public health informatics, still have data management, epidemiology, and Kumar. YouTube film Very presentable. Take calls when I last time. It is not Muthu Kumar, no? Oh, okay, Acha.
Yeah, thank you for the introduction, and thank you, Dr. Sujata ma'am, for the invitation to participate in this program. And good morning, good evening, everyone. Uh, we'll start with my presentation. So I'm going to talk about infrared imaging healthcare. Let's begin. Let me share my screen. Okay. I hope my screen is visible to everyone.
Yes, yes, it
Yeah.
is.
So, yeah. So, yeah, I'm going to talk about infrared-based clinical health monitoring. I'm expertise in infrared-based health monitoring. So, when it comes to health monitoring in assistive healthcare technology, it's one of the important tasks. When we talk about health monitoring, there are two main things we need to be consider. One is a wearable device, and another is a non-wearable device. So when it comes to wearable device, there is a lot of uh, devices which is already in the market, which uses the accelerometer, kinetic sensors, and all these things. So, and when it comes to non-wearable device, mostly it's based on the environment or the ambient based, like based on the temperature or the wind or the air and all these things. So that is also nowadays recent emerging technology which was growing based on non-wearable devices. So when we take wearable devices, it must carry all the time, which causes discomfort to the user, because the people need to wear all the time to track the biosignals. That means discomfort to them, or in case if they got fallen or they get wet in the water, they may damage. So these are one of the biggest disadvantage of wearing devices. And when it comes to non-wearable devices, it's mostly based on environment. So when the environment changes, so that it affects the bio signals. So that is also one of the disadvantages. Like both has multiple advantage and disadvantage. Particularly where we need to use, and how effectively we need to use. Like we can't ignore completely wearable and non-wearable device, both the things which is needed, but it depend on the requirements and uh, the problem statement. So we're gonna see some of the wearable devices, which is like smartphone you always used to carry, and smartwatch you all used to wear it in the rest, and accelerometer, kinetic sensors. So some of the non-wearable devices are the LiDAR. This is one of the recent technology which has been emerged and used in many industries such as automobile and monitoring the forest and all these things. And Doppler radar sensor and infrared array sensor. These are the non-wearable devices mainly used for various industries, and also that can be used in healthcare industries too. So among all those devices, we gonna focus on infrared sensors. Like you should have a question like there is multiple devices which is already there. Why we gonna choose infrared? So infrared measures the heat in the environments and projected in the matrix, then visualize it is a like a image. These see this is an infrared image, and these are the temperatures in the environment which has been projected as pixels. So each pixel is temperature value, and see this place has most highly temperature which was there in the environment. So there is nothing but the person. This is a RGB image and this is the infrared image. So so this is how you can visualize the infrared image, and as I told you already, this has been used in multiple industries, which is automobiles and aerospace and healthcare. So when it comes to monitoring healthcare, there are mainly two sensor has been primarily focused on pyroelectric infrared sensor and thermophile infrared array sensor. So these are the pyroelectric infrared array sensor and thermophile array sensor. So when it comes to pyroelectric infrared array sensor, like it can able to measure the motions at the time, but it can't able to measure the static objects. Is one of the disadvantage when we do monitoring. So mainly this has been used for gas detection and all these things. So when it comes to human monitoring or healthcare monitoring, we need to monitor both the static object and the moving object. So when we go for thermophile infrared array sensor, it has a capability to measure the both in static object and the dynamic object. Like for example, if the person was sitting or like moving or walking or following all these things like or sleeping, so these things can be monitored continuously. So when it comes to the clinical monitoring, how we can like it can be used to measure the heart rate, breathing rate, and body temperature. Using the body temperature, we can able to analyze the heart rate, breathing rate, and that has been analyzed using artificial intelligence algorithm, and it's mainly used in schools to monitor the healthcare. And how this works, like we collect the data and then we do analysis on the data, and we try to discover the health status of the person based on the biosignals, and it can be used for the multiple applications. So like it's mainly used in hospitals and clinics to monitor the patients remotely. With it's mainly used for chronic disease. Chronic disease needs a continuous monitoring. So for example, like patients can't able to come to the hospital like every week or every month, so it makes little painful for the patients or the doctors also. The sorry, doctors has to meet a lot of patients, and it has like too much fast. So when we do this remote monitoring, so doctor can monitor from the patients from remotely, where he's been existed from the home. The patient has been resided in the home. Through that, the device, infrared device, has been fixed in the home. Through that, the doctor can monitor the biosignals continuously and track the chronic disease conditions, and he can update the prescriptions. So through this, it saves a lot of time and lot of resources, lot of human efforts and all these things. So this is one of the thing like very helpful. And real-time monitoring can help to detect many biosignals such as like dental diagnosis, diabetic neuropathy, breast cancer, and personality test, and all these things, which is very helpful. Not only with the infrared, and also we combine with the other signals, signal data or image data, try to find more information from that. We try to discover the continuous monitoring patients status. So through that, like we can able to identify this multiple disease identifications. And then let me tell you, like with the infrared image or infrared signals, so we can able to monitor the blood glucose level for the diabetics patients, and blood pressure level for the hypertension patients, and heart rate and rhythm is also can be able to measure for heart disease patients. And also we can see the oxygen saturation in respiratory distress patients, and with the fever or infection. Recently, this has been become more trending in after COVID. You might see like many places the people started to measure the temperature using infrared cameras through non-contact, and also it is also used to detect the skin disease like melanoma, and also used to identify the neonatal jaundice in infants, and also detect the signs of sepsis in hospital patients. If the hospital patients behave abnormally, they can able to identify using infrared. Uh, and then next, when we come to the remote patient monitoring, it improves the healthcare access, and as I already told you, it saves a lot of time for the both the doctors and patients. No need to fix an appointment, no need to put an effort to come and go, and it saves a lot of time. So when it comes to continuous monitoring, there is something which I would like to tell you, that like infrared radiation helps in pain relief and muscle relaxation and tissue repair and all these things when we have infrared radiations in the home. So that help us for the treatments. And most of the people come across sauna, right? So sauna will help us to improve our blood circulations and the pain management, and also it also uh, help in the effects in the cells and the intermuscles membranes and all these things. It's not only for monitoring, and it also works as a treatment. I'm going to show you how the infrared works. Like this is an infrared camera. The radiation has been sent to the humans, and the human will emit the radiations that has been projected in the image, that has been analyzed by the doctors, and then try to discover based on the information received, like how the patient's disease and all these things. And when we do monitoring, there are two types of sensors which we already discussed: contact space and non-contact space. I'm gonna show you which is the context-based infrared sensors which is available in the market. This is one of the super expensive one. Okay, the this has like not only infrared, it has all other sensors which used to monitor the signals. It is used to measure the blood glucose level and also psychological parameters. So it helps us to analyze the data using the AI algorithm, and send the results to the doctors, which is one of the very expensive one. When it comes to non-contact sensors, we already discussed about pyroelectric infrared and thermophile infrared sensor. That this is cost effective, and it's also can be used as non-contact sensors. It's mainly work based on the ambience environmental changes. So these are the two infrared sensors, which is contact based and non-contact based. Both has various advantage and disadvantage. We can't ignore any one of that, like, because depending on the requirements and the predictions, like we need to use either contact based or non-contact based. So when it comes to non-contact based, it can be easily can placed in the environment, and no need of training how to use it and all the stuff. And sorry for that. And there is no contact with the human bodies, so they can no body fluids, or it can't be erosions has been happened and all this stuff, like it is good for non-contact sensors for monitoring. And these are the examples of non-contact sensors. This is a thermometer, and this is thermophile infrared camera. It's try to detect the temperature, body temperature, and this is try to detect the uh, temperature and projected in an image, and that can be visualize it, and it has more information so that it can be help to identify the pressure ulcers, bedridden patients, and all these things. And there are certain limitations in the IR-based clinical monitoring. Um, the accuracy is always depend on the quality of data has been obtained from the sensors. So if the accuracy the quality is not good, there is a lot of inaccuracy in detecting the disease. And there is certain limitations in the healthcare settings, like uh, we need a people to um, train how to use it and all these things. So it's not suitable for all the cases, like when it comes to emergency or immediate attention was needed. So from that kind of environment, we need a context-based sensors. So the, their IR-based sensor will not work. Excuse me.
Yes.
And also, there is a lot of challenges in implementing, as I told you about the cost implementation and integrating with the existing healthcare, and a lot of privacy and security concerns and standardization, regulatory barriers, and data management analysis, and technical limitations to the sensors and algorithms. So we usually used most of the vital signs we used to analyze AI algorithms, then that needs to be compatible and extract the information from out of it. And also we need to train the healthcare professionals how to use the device, how to collect the device, how to collect the data, and how to visualize the results and how to read the results and all these things. And the patients also ready to accept the technologies which is like need to wearable or non-wearable and all these things. And also there is some certain ethical consideration, whether that can be used, that may cause the damage to the patients or discomfort to the doctors and all these things. And interoperability with other medical devices, if you wanted to integrate the multimodal devices with the as I told you, this one, this sensor has multi sensor has been integrated, that needs to, that interoperability need to be checked. So these are the challenges when we do the health monitoring with infrared and all other devices. Let's see some of the case studies which has been practically implemented using infrared array sensor in health monitoring. So when we the University of Utah Health Hospital in they use non-contact infrared thermometer to measure the body temperature of the patients and the staffs. To that has been integrated with the EHR, electronic health record, to to analyze the staff's attendance and staff's healthcare. In case if the staff has some diseases like fever or some virus things that has been transmitted to the patients, right? So that needs to be prevented from that. So it is helpful for many things, not only for the temperature measurements. Based on the temperature measurements, we can able to do a lot of things that has been practically implemented and currently active in the University of University of Hospital Utah. And another key study is this is used to monitor the monitoring system. So this has been implemented in US to monitor the military veterans. They have chronic conditions like congestive heart failure diabetics that needs continuous monitoring was needed. So telehealth remote monitoring program that has been developed by BHA, Veterinary Health Administration of United States government. That people needs to monitor continuously, so they can't come to the hospital always. So they fix this device to them. Through that, like they can monitor remotely and assess the conditions of the people. Okay, so this has also been currently active. And another is diabetes management program that is used to measure the blood glucose level. This has been implemented in Keio University Hospital in Japan. This is currently working condition, like when the people need to this diabetes patients needs to check the glucose level every time, so they they can't book the appointment and visit the doctor and all these things. They fix the infrared camera, so they just go there and check the blood glucose level. The results has been displayed, and then if it's high, then they need to go and see the doctors. If not, they can come back and book the appointments whenever we need it. They can check the doctors. This is the real time things which has been existed in the hospitals. And also University of Michigan has been implemented the hypertension management system. They tried within the uh, students and patients, but not has been practically implemented. It's not currently online. Okay, so it's used to measure the blood pressure and things, but soon it's going to be on live for the whole hospital. And these are the case studies which they has been currently use the infrared sensor for monitoring the biovital signs. And case study of our work, like we try to build an activity detection system using infrared array sensor, which is low resolution array sensor that has been integrated with our main purpose is to develop a low-cost monitoring device. So we integrated with the Raspberry Pi with the camera and infrared sensor together. It's try to monitor the person at the home and whether they have abnormal activities such as fallen or things like that. So we fix the infrared array sensor, one on the ceiling and the one on the wall. We try to combine together and try to monitor. Our system able to achieve 0.97 accuracy. We use various algorithms such as CNN and LSTM, and we tested in different environment. And when we change the environment, there is like a lot of heat difference will be there, temperature difference will be there. There will be a noise, and there will be due to the noise, they will get a blurry images. It's hard to identify some of the activities. For example, the activities such as like lying or falling, which is similar, right? So it needs a continuous monitoring. So that kind of activities are hard to identify and blurry and noisy images. So we thought to solve that problem and applying various AI algorithms and super resolution denoising and all these things. And we try to improve that, and we got a highest accuracy of 98.12%. So I'm going to show this work how we did it on hands-on training. Okay, so here we reduced to the only ceiling sensor. We remove the wall sensor. From the single sensor, we can able to achieve 98.12 after we did multiple pre-processing techniques such as super resolution and enhancing the image. So this is how we optimize, and also we can optimize the model to run on the low power devices such as this. This can be currently deployed on the real-time environment. It works good. You can able to achieve 98% accuracy. And also another case study which we would like to emphasize here is sleep apnea management. So through the infrared monitoring, the same monitoring can be used, the same device monitoring can be used for sleep apnea to identify the people who have sleep apnea. This is while sleeping. It is mainly helpful for maintain the breathing patterns and all these things. So the people who don't know what is sleep apnea, this is a normal sleep, this is a sleep apnea. When you sleep, the tongue will be there, the soft palate will be here, the vulva has been increased and closed. So when you started to breathe through the nose, so there will be breathing block will be there. So you will get breathing through your mouth. So you'll get mouth will be open and you got a snoring kind of thing. So that's something to monitor. And I would like to discuss about the potential benefits of health providers. Health providers are nothing but the doctors. As I already told you, it increases the efficiency, it reduces the remote monitoring, reduces the resources, and puts on appointments on all things. And also the benefits to the patients. Patients no need to come to the hospital and they can do their work. It will not affect their regular routines and all these things. And also it helps to maintain the disease management and improve the quality of life. And there are also the limitations to the health provider. As I told you, the quality of the data is depend on the accuracy. So if the quality of data is good, the accuracy will be good. If it's not, like, then the false detection might be happen that leads to several other problems, and also some like kind of need to train the doctors how to use the device and how to view the results and all these things. These are the limitations which exist. And the potential limitation for the patients is like there may be a concern about the data which is collected, where my data was going, where it has been shared, and all these things. So for all these things, there is a regulatory considerations. One such regulation I would like to talk about is Health Insurance Portability and Accountability Act, which is called HIPAA. They was handling like healthcare data, like what are the privacy concerns, how to deal with the data, and how to handle, how to store, and what things need to be shared and what things need to be shared, and who can access, and all this regulation has been defined by the HIPAA. There is a lot of such regulatory body which is there. Like it's one of the HIPAA is one of the regulatory body which need to mainly handling all these things. So when it comes to comparing the other monitoring technologies such as ECG, blood pressure cuffs, and all this, they are as an advantage and disadvantage. Like non-invasive things as good advantage, like without contacting the patients, we get more information, and it also has limitations based on the accurate data collections and all these things. But when you go for traditional monitoring, it gives more accurate data, more accurate predictions, and it's well widely used in healthcare. That's still now they are using to get the higher accurate things. And there is a future research direction when we use, like we can try to improve the AI algorithm analysis on using the low information, less information from the data, and try to improve the performance, and also try to build new applications, like try to build new exploring new detection using the temperature environment from the patients. So that's it. Thank you. And we would like to start hands-on experiencing. I would like to show you how to process the infrared image, and how to detect activity and all these things. And if you have any questions or anything, please feel free to let me know before starting the hands-on training. Any questions? Any questions? Any questions,
Okay, you
please?
just start your answer.
Okay.
Probably you'll be
Okay.
getting question once you start
Okay.
your
Okay.
answer.
Yeah. I hope my screen is visible. Yeah. Yeah, it's visible. Okay. So, we start from the basics. First, we start with the installation. Most of the people uh, might not be familiar with how to start. Okay, so we'll start with we're gonna use programming language called Python. Okay, and using the Python, we try to analyze the data, and also we do the machine learning, how to run the various machine learning algorithms, and how to import the data, and how do we process the data and all those things. We start from the beginning, like how to set up an environment. Okay, so there is environment setup repository called Anaconda. So you need to download this Anaconda for Windows. There is, it's not only for Windows, it has Windows, Mac, and Linux. So I would highly recommend uh, when you do these things on Linux. Due to my resource constraint, I use the um, Windows system. So when you people really want to work with the highly um, biomedical data, please go forward the Linux. That will be more helpful. Okay, so download this. Once you download, you'll get a file like this. Yeah, like this. Then once you install, you will get a page like this. I'm gonna navigate up. So the people can. I hope the people are not aware of all these things. So I would like to be which environment which is very familiar to the very basics people. So I would recommend to use the Jupyter notebook, so the people who have no background, so they can use this Jupyter notebook, which is very helpful for them and easy to run the code and easy to understood. And when you launch this one, you will get a page like this, and you can see the files over here. And there is a file, which file you wanted to open, you can open like this. And then you can start creating new folders like this. Like click here new and create a folder or terminal text file, or you can create a notebook. So when you wanted to create a notebook, new notebook file, you just click the Python 3. So when you click this, the new notebook file will be created. So here you can type the code, like for example, like this is a package we try to import. NumPy is a package of Python. So we try to import the package. It used to do the linear algebraic calculations and work with matrix and all these things. So when you wanted to run this cell, like you can type the code here in this cell and you can run only this cell. Okay, it will be run. Like for example, if you wanted to type this like 2 plus 3, you get results here. Okay, this is how you need to run and execute the Python environment using a Jupyter notebook. I would like to show you the next infrared, how to import the infrared image and how to process the image and all these things. So there is a lot of packages which is there. So you need to install the packages using this, like go to, I'm gonna navigator, go to environment, and you can click this and you can search the packages. Like for NumPy, it deals with linear algebraic calculations, and to visualize there is a package called matplotlib. So that's already installed. Okay, you just click. For example, if you wanted to click this and click install, it will be installed. Like, let me show you how to install. Like this, if you apply, it will get installed. So there are a lot of packages which is available only when the requirements, like what are the requirements, like you need it. Based on that, you can install whenever you need it. No need to install all the packages. But NumPy, Matplotlib, and Pandas, and these packages are the common packages we needed for all the processing biomedical images, not only for image data, the signal data, and also the data such as textual data, all these things. So basically all the data is being converted into array, then the operations will be happen on that array, single dimension vector, 2-dimension vector, all these things. So usually now we're gonna deal with the infrared image. So infrared image is a 2-dimension array. Okay, so we're gonna see that one. Okay, so yeah, and also you can use install packages using through Jupyter Notebook also, like using a pip install NumPy, Matplotlib, OpenCV, Python. OpenCV is mainly help to deal with the image processing. Okay, so like how to import the image and how to change the image. So these things will work with the OpenCV. Matplotlib package is mainly used to visualize the image or visualize the graph and all these things. NumPy, I already told you about, deals with the linear algebraic calculations. Okay, so this is how you can install through the cell, and also I have an infrared image. This is the infrared image was taken from the thermophile infrared sensor. Okay, the person has been lying on the ground. Okay, so we gonna analyze this image by various image processing techniques. So let's get into it. So first we load the data. Okay, so we import the package computer vision OpenCV. Okay, OpenCV Python. Okay, and import OpenCV, and also we need to import the Matplotlib as a plot. Like so, Matplotlib as a plot PLT. That means like you can call this packages using this name, like PLT. We will see in the next thing. Okay, so we declare the variable data and CV2 in read. It will read the images from the location, the file name. This is the file name, IR image data, and then it will check whether ImRead is a grayscale or RGB image. Okay, so it will import the thing as a okay, and then next, once you imported the image, we need to visualize the data. So we use a CMap function, which is it has like infrared that help us to visualize the heat map. Okay, so when the temperature is high, it shows this color. Like it's try to differentiate the temperature using different colors, like from 0 to 220. Okay, so this is how you need to visualize the IR image, like the heat map. So once you visualize, once you import the image, and we check whether the image, like our image, has been imported properly or not, to check and visualize. So see, this is the image we imported, and it is exactly look like see. Okay. And after importing the image, we try to do some of the image processing techniques. We try to enhance the image to make it more visible. Like we use the histogram equalization. This is one of the image processing technique to enhance the image. Well, this technique has been inbuiltly built in the OpenCV package, so you no need to write code for this package. So you can just import, you can call the OpenCV, and from there you can request a function called equalize histogram. So equalize histogram, and you need to check the data type of the images. You int 8 and after that, like plot im show equalized, and CMap is used to visualize here. And you can plot title, you can make the title here, equalizer IR images you can give here, and plot color bar and plot image. So this is nothing but this is the color bar. Okay, so when you plot dot color bar, when you give this, like you'll get this one. Okay, and when you show the plot in show, okay, and the image has been shown. Like see, this places has been enhanced. So these are the places which has the highest temperature. This is how we do the image enhancement. We used one of the technique called histogram equalization. So you no need to go to every time to run the cell. Click here, and also you can use shift enter to run. This is a keyboard shortcut to run the cell. Okay, so and also there is things like you can add the cell, and you can cut the cell, and you can copy the cell, and you can move the cell and move up down like this. Okay, so these are the things. Okay, next we gonna go for Gaussian smoothing. Okay, okay, this is a Gaussian smoothing. This has been moved. Yeah, so this has been moved from here. Like for example, you can move up. This is histogram equalization. This is Gaussian smoothing. Okay, this is another technique from histogram equalization. There is another technique called Gaussian smoothing. This is another technique. Like you don't need to write code for Gaussian smoothing. This technique also inbuilt in OpenCV. You just call the OpenCV package. From that package, you can call the Gaussian blur. Okay, so basically how this works is like it's try to enhance the uh, whole image, is like it's try to blur the main part, like all the pixels, so it's try to make it blur and make it more enhancement in the regions. And see this one, it's try to work on all the pixels and make it blur. So the same way you can use the uh, higher data and try to show using the plot and CMap Inferno, and then you can make the title and show the color bar and make it see this one. Like, can you see the difference between histogram equalization and Gaussian smoothing? So Gaussian smoothing is much better than histogram equalization. It doesn't mean that like it will be good at all the time. Sometimes this histogram might be better, and sometimes it's a Gaussian blur will be better. It makes it more blurred so that you can enhance the image much more. And our next image processing technique called thresholding and segmentation. We try to do the thresholding and segmentation. There is different types of um, thresholding techniques, which is global thresholding, adaptive thresholding, and all these things. These are the basics image processing techniques, global thresholding. So like for example, thresholding is nothing but we try to differentiate the background from the object. So it fixes the, for example, 127, 255 is the total one. So fix the thresholding as 127 and then try to make the separate the background from the object. So through that, like you can call the global thresholding function, which has already been inbuilt in OpenCV. So OpenCV is one of the packages that mainly deals with the image processing. It has like most of the algorithms has been inbuilt. You can call the functions the same way, like you can fix the thresholding. And when you do this CV2 threshold binary, so it shows in the grayscale image black and white. So it try to extract the object and put it in from the extract the from the background and try to identify the object. This is one of the thing called thresholding techniques. Okay. And another is called adaptive thresholding. Adaptive thresholding. So adaptive thresholding works on like particular base. Like see this one, see this. This is the region base. Based on this region, we try to fix the uh, thresholding values, and then they try to go through the each pixels and try to differentiate the black and white and extract the features. So this is how it works. Like for example, like here we used CMap grade. Like it has like multiple options in Inferno. It's used to display the heat map, and gray CMap gray is used to display the black and white, like which is grayscale image. So these are the techniques, adaptive thresholding and global thresholding. And once you extract the background from the object, like next we need to do the analysis and the measurements on the image. So what we do is we try to extract the contours, like it's like try to find the corners of the object using fine contours. And we already had a threshold has been fixed, and then try to identify the edges in the object. Okay. And after that, like we draw the contours, like of the edges. When they found, they try to connect through the lines. So this is how counter images is being connected to 0 to 0 to 255 and so on 2, and then it has been shown in the counter images. Okay, so once you extract the edges of the objects, then you need to measure the how many pixels within this has like high intensity and low intensity. So that is nothing but measuring the area of detector reaches. So area of count is like 15 pixels and 8 pixels and 89 pixels and 0 pixels, which is mostly found, and then 5 to 5 points pixels, which is being found within this thing. This is how you need to analyze on the simple single image IR image to do the image processing. These are the techniques. Once you load the data, then visualize the data, and then enhance the image, and then try applying various histogram equalization and Gaussian smoothing, all this thing. Once you enhance the image, then you need to segment it, thresholding through the extract the object from the image. And after that, once you extract the object, when you try to find the boundaries, and then from the boundaries you try to detect, measuring the areas of how many pixels which has been related to that objects, and all this thing. This is the basic image processing technique from the image. Okay, so if you have any questions, please feel free to ask me in this one. Okay, any questions? Okay. Okay, so then we move to the next. This is the basics of image processing techniques. So next we gonna do things like how to do the activity classification using this infrared image. So that also we need to do the pre-processing and all these things. Once we pre-process and label the data, and from there we need to do classification of each activity. When it comes to the multiple like continuous sequence activity, we need to do the sequence classification. Like for example, when you walk, how did you identify the walk? You need to monitor some time of the subject, and then you need to tell the guy is walking, and then there is falling, then you need like continuous monitoring. That kind of classification how we can do, we'll see that in the next one. Okay, so if you have any questions, please feel free to let me know so that we can move to the next one. Any questions?
Yeah, few questions are there in the chat box.
Okay.
Can you provide the link for dataset?
Yes, I'll
Parveen Malik.
link for the data. So can you share the Jupyter notebook that you are showing? Yes, I can share. Give me a minute. How can I share it? Share it in the Google Drive. Is that okay?
Can you share the picture about the notebook that you are showing? Yes.
He do that's it just last session also we do. Dr. Kumar Dron shows কথা কব না I will do this 4 we the same person for having look at this makeup and
Hello, Anthony, is everything okay? Hello.
Sir. Is everything okay?
Hello.
Hello, ma'am.
Hello.
Yes, ma'am.
Any problem in our side?
No problem.
Okay. Then he will join. Okay. Dr. Muthu Kumar will present his experiment. Just he is trying to say at the court and data set.
Yeah, sorry for that. Give me a minute. Like I have a.
Technical problems.
Do you have any problem, Muthu Kumar?
Yeah, wait. I was trying to share the data set so that people can try. I have problem with the internet. Like, give me a minute, 2 minutes. Like,
Okay, sure.
You have any problem? You didn't question for like अगर on शिफ्ट में तो I don't know this actually my professor in computer science doctor of computer science are doing any you have any problem? No problem at all. Sorry. message now. She just like doing exclamation mark. That is not false. It's very Oh no. Sir, एकता भी presentation में आजिला ना बोले तो दिखा ये like those strangers ना if picture comes I have to
Kumar, can you hear us?
Yes, I can hear. Like I was trying to share the data set. I have like my internet. I don't know like why it's. I'll share at the end. Okay.
Okay, no problem. You can continue, sir, please.
उसका network का problem आ रहा है हाँ क्यों भी करने के लिए सर पाला है मैं usually WhatsApp पे मैं WhatsApp मैं what is it your कभी कुन account है सर department है क्या कभी सीधा ओ क्यों Gmail ने पता ही दिया नमस्ते
Hello, Dr. Muthu Kumar. Hello.
Hello. Ma'am, Sujata ma'am. Yeah, sorry for that.
Can you
Like,
start?
Drone will
Okay.
start the presentation.
Okay, sir.
Yeah.
Drone की भाषा होती है ना drone की pose ना अच्छी है set for किया हुआ है
Good afternoon, ma'am. And at the outset, I would like to thank the organizers of this FDP program. My name is Dr. Kumar Dron Shrivastav. I have a doctorate in public health and I'm a master's in computer application. So, and now today I will start talking about my doctoral work and current research, which is based on the early detection of cervical cancer. So, I'm going to show the presentation now. One minute. Okay, so is it visible now?
Yes, it is. Please go ahead.
Thank you. So today I will be talking about the development of a robust image analysis tool for detection of cervical cancer. As you know, it is one of the most lethal cancer, and in India it is the fourth most common cancer. Sorry, in worldwide it is the fourth most common cancer worldwide. Approximately 185 women die every day, and 8 women die every hour. A woman dies every 8 minutes just because of this disease. And the good part about this cancer is it can be cured up to with 93% accuracy if it is detected in its earliest stage. These are some stats from WHO, which shows the progression of, presence of cervical cancer, which is approximately 604,127, which contributes to 3.1% in both the sexes. And in India, it is now at the very alarming stage and subsequently growing at a very rapid speed. So why we are doing this research and why we have been working on this problem since last 7 years? Because cervical, no disease, no doctor can just randomly says that you have this disease or you do not have this disease. There are some concrete parameters based on which a clinician makes the diagnosis. In case of cervical cancer, there are multiple modalities and multiple parameters based on which precancerous or cancerous lesions are diagnosed by a clinician. If you see this these images in CIN1, CIN2, CIN3, these all are the images of cervix, which is the lower part of the womb. And based on the morphology, its texture, its color, its histopathological analysis, the cancer or pre-cancer stage is diagnosed. These are some early warnings and signs, warning signs of pre-malignancy or malignancy, and which can it can be, if the information is disseminated at community level, it can be treated in a very early stage, at a very early stage. Like I said, you there is a 93% cure rate in case of cervical cancer if it is detected in its early stage. There are some preventive measures that can also be adopted, like sanitation, hygiene, immunization. There are multiple vaccines available even in India. Indigenous vaccines has already been developed for both sexes, male and female, for for HPV, which is the most common, which plays the crucial part in the progression of cervical cancer. But I will focus on mostly on the development of algorithm that we have developed for the early detection of cervical cancer at community level. Why this disease is very prominent in our society? Because of the lack of awareness, the social stigma, because no one woman generally talks about it, and misinformation is spread among the society, which leads to the progression of this very lethal disease. Let me tell you some background about the progression of cervical cancer, starting from the normal cervix and the infestation of HPV, infection of HPV, which is human papilloma virus, which is the contributing factor or the risk factor or causing factor for the progression of cervical cancer. So there are multiple stages in which the HPV progresses, and it forms the basic for the progression of cervical cancer. There are multiple tests available to diagnose cervical cancer, mainly to identify the presence of HPV. HPV, there are multiple strains, multiple types of human papilloma virus. More than 100 types of human papilloma virus are present, but out of all those, mainly HPV type 16 and 18 are major contributor for the progression of this disease. At present, we have multiple problems and challenges with respect to the early diagnosis of cervical cancer. Why we chose this disease and the methodology, the reason behind it was that if we do the community-based screening of women using non-invasive techniques, then it will be very useful for us to develop algorithms, computational platforms, and community-based information dissemination using AI and IoT devices, so that the right message can be spread among the women at community level, and with least resource. When we talk about the patient to doctor ratio, especially in India or LMICs, we have very disproportionate average. And to mitigate that problem, we can use computational platforms and AI-enabled tools and techniques to solve this problem. Uh, Let me tell you the basic two modalities which are used for the screening of women for the detection of pre-malignant or malignant. Malignancy means to say carcinoma. So there are two WHO accredited methodology. The first one is Pap test, and the other one is colposcopy. We started working on slides initially in our initial research, but we came across that Pap test is more resource oriented and cost oriented. It requires exhaustive expertise and healthcare infrastructure to do the screening. While in case of colposcopy, we need comparatively less resources, only the colposcope and a trained gynecologist or a trained health worker who can just acquire the image of this cervix, and based on the appearance in textures and texture, although in fact there are multiple other parameters also that are taken into consideration while doing the analysis, but at least if we use this technology or use this methodology, then it would reduce the number of false positives and false negatives in doing screening at community level. I will move to the moves next slide, which is, in these days there are multiple companies which manufacture colposcope, handheld colposcope, which can be previously 5-10 years back. It was a very resource oriented and healthcare center oriented process where designated room, designated lab, designated doctor, a designated pathologist, and multiple other infrastructure requirements were required. But nowadays, we have handheld colposcope. Showing the image of Israeli-based company, that is Mobile ODT, which manufactures the colposcope, which can be put it at which can be taken to the community, and the images of the cervix can be acquired in almost real time. The image plays the crucial part in colposcopy because it is a non-invasive technique, so no anesthetic or no any other resources are required to acquire the image of the cervix. Even in remote areas, in the remotest areas of India or any country, the device can be taken to the community, and in a private room or private setup, the image can be acquired from the community. And using our algorithms, at least the normal and abnormal segregation, the tagging of normal cervix and abnormal cervix can be done in almost real time. Here I am showing you two pictures of confirmed carcinoma cases. You can see in colposcopy also there are two methodologies used. First of all, to stain the cervix so that the exact picture of the cervix can be acquired. The first one is VIA, which is visual inspection with acetic acid, in which acetic acid, 5% acetic acid is used to stain the cervix. And based on the morphological features, the clinician diagnose whether the cervix, the text, when its colors changes to mahogany, from mahogany brown to mustard yellow, the progression of the disease is diagnosed by the clinician. The other one is VILI. This is visual inspection with Legol's iodine, which is another chemical. It can be it is which is used to stain the cervix and do the diagnosis part. In our methodology, we used R as the programming language, MySQL as the database repository, Linux as the base platform, because we wanted to also safeguard our data, because these images are very crucial and sensitive to acquire from the community. Even in the hospital settings also, we went to the hospitals like Delhi State Cancer Institute, Batra Hospital, and even we did the health camps also in multiple rural areas of India, and acquired the images from the community. So as you can see, we also calculated the sample size, what would be the minimum size, and what would be the our target population, what would be the exclusion and inclusion criteria. Like we excluded women who went under hysterectomy, and who were pregnant women. So there were multiple exclusion criteria for women to come into the consideration for screening. And the three major idea and concepts that we kept in mind while starting our research was the cost should be minimal, so, and it should be very fast, robust, so that the false negative and false positives can be could be controlled. That's why we used all the open source platforms like R, Linux, MySQL, and other tools and technologies. Initially, we did not have the real, primary data from Indian specific women. So we started searching the online repositories, and there is a repository called Intel Kaggle Mobile ODT repository, from where we acquired the images of 1481 cervigram. Cervigram is the image of the cervical lesions. So we acquired 1481 images that were randomly categorized into ectocervix, endocervix, and the third part. Based on our algorithms, when we started tagging the images after training the algorithms, when we started tagging and classifying the images, when we ran our codes on those images, then we were able to classify the images into absolute with almost 100% accuracy. But But I mean, you can see the classification. You must be aware about the machine learning, and Muthu sir has already in detail described about the machine learning, deep learning, and
No, 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 no. He's speaking. No, press mic, press mic. Press the mic, yes. Sir, can you mute yourself?
Hello?
Only he can, he himself can. No, no, it's not.
Hello?
Sir. No, it's fine. Ma'am.
Yes, ma'am, you are audible.
Okay, please continue.
am I audible?
Yes.
Yeah.
Okay.
Sorry, sir. Yes.
Hello.
Hello?
Yes, sir.
Am I audible now?
Yes,
Please continue, sir.
Okay. So we initially we searched multiple algorithms and applied while doing the basic research for pre-processing, data analysis, matrix calculations, and various other steps to develop the algorithms. And after comparing multiple algorithms, we were able to at the end get this very novel algorithm that is called EMD, Earth Movers Distance algorithms, which is also used for the differentiation and classification or comparison of two different sets of data, and find out the perceptual similarity and dissimilarity between two distributions. So at the end, the 2D images are nothing but the repositories of data sets in terms of matrices. Then you can see this is the layout of, I mean, this is the screenshot of the R environment in which the left side is the code section, the other one is plot section where you can visualize the images. In the right side, right upper side, the environment section where all the variables are stored. So we rationalize the processing in different categories. The major reason why we chose was the pre-processing of colposcopic cervigrams, where we were able to do it in almost real time. The advanced image analysis capability of R, as you know, R is nowadays being used for exclusive and extensive data analysis, and incorporation of morphological features are already there in R. Fast processing, and the most important part is it is open source. So if I talk about the workflow of the whole algorithms, it starts from the acquisition of cervigrams through colposcope. So as I told you, colposcope is nothing but an image acquisition device which is used, I mean, which is equipped with white light and other peripherals to acquire the image. Once the image is acquired, the first part is to do image noise removal for its pre-processing. Then its cropping regions of interest, because most of the part in the image that is acquired with the colposcope are noise and other artifacts that we need to remove before doing the real processing. Then we did matrix calculations so that the test images or the threshold images with the test images, I mean the threshold images and the test images can be of same dimension, so that we can match the individual pixels with other pixel, and based on this we can generate unique number, and based on that number the image is categorized whether it's normal, whether it's abnormal. If it's abnormal, then up to what extent it is abnormal. I will in next slides I will show you how does it really works. Then the color coding of the images. So while doing the analysis by any gynecologist, it is more easier for them to segregate normal and abnormal regions. Even for biopsy, the algorithms enables the individual pathologist or the clinicians to isolate the area from where the tissue has to be taken out for the biopsy. And as you can see, these are the three images in which the earth movers distance have been applied. The first one is the normal image, the second one is with grayscale, and the third one is with areas of interest. In the later images I will show you how does it really work. As you can see in the right sections, there are areas which has been contoured in yellow, and blue sections. Yellow primarily indicates, and in the at the bottom you can see 0.2, 0.4, 0.6, 0.8. It is the level of severity from where the pixels, I mean the abnormality of the lesions are identified. Now you can see there is one matrix, there is another N52 versus other images. N here is the number of cervigrams. Suppose I have acquired one image from individual woman, then that image is termed as N1. Just like that, N2, N3, N3, N4, N5. So initially we acquired the data sets from the Delhi State Cancer Institute for around 100 images, out of which there were multiple, approximate images. They acquired more images and the numbers increased to 300. So out of 300, 84 were normal, and some were abnormal, some were pre-malignant, some were confirmed cancers, and all these diagnoses were done by the clinicians only. Then we first of all, to train the algorithms, we ran the code on we run the code on our normal images. Among normal images, we had to calculate a threshold image from which we could compare other test images, and based on the EMD values that is generated in terms of numbers, absolute numbers, we could categorize the image into precancerous, cancer, pre-malignant, whether it's CIN1, CIN2, CIN3, cervicitis, or any other category. So as you can see, this is the layout of the mobile ODT colposcope. The image was acquired on this date. The image was acquired by Dr. Selibatra ma'am. The diagnosis was made by Selibatra ma'am as cervicitis. There were other, I forgot to mention these things, that we did not just focus on computational platform. We also acquired the socio-demographic features and other parameters based on the questionnaires and other patient doctor queries, and we did statistical analysis also to come to the conclusion that what are the major factors that contributes for the for the progression of cervical cancers. As you can see, like I said you, this is the first one is the original cervigram. Then with the help of the algorithms, we were able to crop the image and crop out the region of interest, because this is the area where the doctors focuses. And for pre-processing and a specular reflection, as you can see in this image, there not in this image, but there are multiple images where white light reflections are there, where there are multiple noises. So to mitigate those problems and do the noise removal, we applied these steps in developing the algorithms. And in the next this slide, you can see there if there is any noise in the original image, then based on the three components, red component, green component, blue the other component, we were able to remove the specular reflection based on the HSV value, that is hue, saturation, and value format. Yes, this slide will give you a clear picture. You can see in the original image there are multiple white light portraying on the image. So for doing the exact analysis or accurate image analysis, we had to remove these white lights from the cervigram. So we applied these algorithms, and after the pre-processing is done, you can see in the final image the white light in the original image is gone. Now the diagnosis can be, now the image is fed to the algorithms on the oncometer for further processing. You can, these are other images in the left side. You can see the original image on the right side image. After applying the algorithms, you can see the noises and white lights are gone. Initially we did the matrix calculation also. So here you can see the numbers that is there as 33.744. This is the number of EMD value, which I will show you in a 1-minute video. How does it calculate and compute or classify the image into type 1, in precancerous or cervicitis or any other category. This is another example of the raw images, how it is converted into, threshold image, or sorry, how it is converted in its pictorial, visualization format, so that the area of interest can be kept into focus, and the doctors can do the analysis or take the tissue from the cervix. This is a scale. This is a new scale, a novel scale that I was talking about. It is a scale. It is ohm the oncometer. Like you have heard about thermometer. How thermometer works? When the temperature is above 100 degree Fahrenheit, the patient, the subject is diagnosed that you are having fever of more than 100 degree Fahrenheit. We also try to incorporate the same logic behind the development of this oncometer, which is a novel. This kind of a scale is nowhere present in the world. The scale is developed using the EMD value that is generated after the comparison of random image or any test images with our threshold image. Threshold image is the image that we got after the calculation of multiple normals images. And based on this image, you can see in the right side there are different categories and there are ranges that we observed after the calculations. Although we have a limited sample size of around 500 for India specific women, out of which we got this classification by the clinician that this is the normal category, this is the abnormal. In abnormal, there are Nabothian cyst, vaginitis, cervical erosion, polyp. Then the next one is cervicitis, then precancerous, then suspected cancer. And then we also incorporated more images and verified it with the gynecologist that yes, these categories these images are exactly, it falls into this category. The accuracy initially were 77% for the first 300 patients. For the first 300 subjects, the sensitivity were 83.56% and the specificity were 59.25%. But for the first 300 images, when we improved number of images, like Muthu sir told, the accuracy or the performance of any AI or computational platform is dependent on the number of training data sets, how much enriched or how much data is available for training data sets, that it covers any versatile or any variety of new images and generates the results in almost real time. These are other socio-demographic and epidemiological features that we acquired from the study participants based on the validated questionnaires like age, education, occupation. The concept was to identify that is there any association between education and the progression of cervical cancer, is there any association between occupation and the cervical cancer, likewise socioeconomic status, marital status, menstrual conditions. So we also included in our studies all these parameters. Like I told you, we adopted colposcopy in place of LBC. LBC is the new technique that is used in place of Pap test. We used colposcopy to get the data from the community and do the analysis. Okay, so in this slide, you can see there are two sets of images, two sets of different stages of images, A, B, C, D. In the right hand side, A, B, C, D. So in the left side, the image is, you can, if you focus on the image or concentrate on the image, you can see the cervix is of normal. In the right hand side, the cervix is of abnormal category. But you can visually see or diagnose, or a clinician visually see and diagnose. When it comes to the computational part, all these things are done computationally using EMD and ohm the oncometer. So in the left image, the A is the normal one, the B is the pre-processed one, the C is the contoured, the cropped image, and D is the color-coded image. In the D section, in the left-hand side, there is no yellow regions as of now you can see. In the right sets of images, you can see A, then B. B is the pre-processed, C is the cropped, and D is the final color-coded image. In the D section, you can see multiple yellowish region. These yellowish regions shows the level of abnormalities present in the cervix. So all these image processings are done in R using EMD and other algorithms. I mean, in these slides, I forgot to mention again these things, that these images are VIS stained. So we try to include all kind of parameters, all kind of methodology. We took into consideration all possible varieties or all possible I mean conditions that could be taken into consideration. This is the slide in which you can see the staining mechanism is used is VILI, that is visual inspection with Lugol's ID. In this image, the image are VIS stain, means visual inspection with acetic acid. In these images, in these sets of images, the images are stained with using VILI, that is visual inspection with Lugol's iodine, because I mean, we went to multiple clinicians to get their opinions, and they said that Dron, if you do this analysis and do this computational works, there might be some biasness or error, because in some cases, if there is any infection present in the cervix, then also the computer will show that it is abnormal or it is precancer, when although it is just an infection of some STD or anything. So to mitigate those problems, we also acquired the images stained with leukocytin to overcome these problems. And again, these are the parameters that we acquired while doing the analysis. Question-based parameters, question-based questions that we collected from the individual study participants. And this is the data on which we did the specificity, sensitivity, and accuracy calculation, like true positive, true negative, how many were false positive, false negative. So based on the sensitivity, specificity, and accuracy were calculated. Now I would like to show you the video how the whole system works in reality. So is my screen visible now, ma'am? Anyone?
Yes,
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 okay.
yes.
Okay. So this is the screen recorder through which I already elaborated how and why we use this methodology to acquire the image of women's in remote areas, because it's handheld and very portable machine. We are also trying to, although I mean overcome, because there are limitations of image quality as well. The colposcope that we used, I mean the clinical grade colposcope that we used had only 13 megapixel, although it had 32 x zooming capacity. But we are trying to improve the image acquisition capacity of the colposcope in consultation with multiple lens manufacturer companies like Canon and other companies. So that, see, the idea is to gather maximum amount of data contained in an image so that we can do the processing more exclusively, more extensively. So I mean, this is the background of the proposed algorithms. And now I'm going to introduce the AI-enabled cervical cancer screening tool that is called OM, the oncometer. Oncometer is the full form of OM, which is a novel scale. And in this scale, in remote areas, we have, as I told you, the three main visions behind development of these algorithms was one, to make it more reliable, more robust, and more user-friendly. So you just need to upload the cervigram. The system can be deployed on web-based application, on Android-based application, and the same can be used and utilized by ASA and Anganwadi worker in, I mean, trained medical professionals in any remote areas. You can see in this image in the left side, the codes are there. The calculations are there to match the opacity of time. I have already calculated, I mean run the algorithms and did the calculation so that the minimum time can be utilized while doing the analysis. You can see the image here is the hand of a gynecologist which is taking the image of the cervix. It is a non-invasive method. No blood is released while doing this analysis. And you can see how the image has been cropped. And there are multiple other things that we have all, done. You can see in the left side, the figure is 89.98561. It is the value that is generated after the calculation. And like I showed you, like I said you that in case of thermometer, if the temperature is above 100°F, then the patient or the subject is diagnosed with fever. Here, in case of precancerous or normal or abnormal cervix, the threshold value is 26.78. So if any image after calculation produces the value of more than 26.78, then that image is considered as abnormal. So the patients or the subjects is intimated that yes, you have some abnormalities in your cervix and you need to go and see a doctor or do further analysis. So this is a very short time calculation that can be done in almost real time in any remote location using the least requirement. And this is the scale that for which I was talking about. The normal range starts with 0 to 26.78. So you just need to upload the cervigram. The system will do the analysis and produce you the EMD result. And based on the result, the system automatically classifies that whether it's a normal or abnormal cervigram. And again, one second, what happened? Okay. So this is the chart. The result is cervicitis. It also gives the tagging of whether it's cervicitis, whether it's normal or it's abnormal. Now let's get back to the original slide. We have also copyrighted. I would also suggest others, developers and programmers and AI users, whenever you develop any algorithms or develop any model or do any computational analysis and it is unique and for user acceptance, then you must go for copywriting. Then your the codes that you have developed or the system that you have developed will be known, will be registered legally in your name or in firm's name. These are some papers. We have also published the same results in multiple journals of high impact like Applied Sciences and Cancer Controls and other journals. So with this, I would like to thank my guide, Dr. Rajiv Janandan sir, Dr. Priranjan sir, and Dr. Preet sir. The another thing that we did, for, like I said, you being a public health professional, our job is to go to the community and do the preventive jobs. I mean to say, when our job starts when the disease has not yet progressed. So to do the to acquire the information from the community, we are always in a we are always in a fashion to use technologies in any possible manner so that the information can be acquired from the community with least resource requirement. So here you can see we have used Google Earth Pro. So to go, if we acquire information from any, or we have to showcase that yes, this is the pocket where this type of disease or this the prevalence or the incidence of this particular disease is very high. Then using Google Earth, we were able to, we can showcase our data, or we can just create a repository of all the relevant information at one place, and further we can use it also. So these are the repositories of ICMR where the cancer cases and other informations can be. So it is a kind of tool that can be aggregated with the system that we have also used to develop the system. So with this, I would like to conclude my presentation and will be happy to take any questions from the audience. Thank you so much.
Thank you, Dr. Dron Shrivastav. Now I request the participants to post any query.
Question answer चाहिए.
Okay, can I ask a question?
Yeah, sure, ma'am.
I have a, Actually, at the last part, you explained that you'll be, location-wise, you can collect the data.
Yes, ma'am.
Okay, you can use the Google Pro.
Google
To
Pro, ma'am. Yes, ma'am.
locate. But
Yes,
how
ma'am.
did you? Yeah. How do you know that the people there are affected or having this kind of problem?
How, for that, we need to do the community-based screening programs, ma'am. So, whenever we do not have a kind of mechanism right now regarding the repository that this is the lat long or this is the pocket where where the government needs to focus exactly on this location. So, using Google Pro, if we acquire the information from the, this is a conceptual program project that we have developed, ma'am.
Okay.
So
Okay.
if we get the information from the community or we have the
Like
resources,
you can prepare
yes, ma'am.
some questionnaires
Yes,
and
ma'am.
can
Yes,
distribute
ma'am.
it.
Do the screening. If we get the connection from ASA and Anganwadi worker who are available at the ground level,
Uh-huh.
then we can acquire the information in almost real time and on daily basis using the dashboard and other technologies. We can produce the evidence and give it to the policy makers that, sir, these are the areas where you need to focus. This is the area of this epidemic. I mean, this disease and this disease. So you need to, relocate your resources to this particular location regarding this, especially for this disease.
Okay.
Yes.
Uh, Actually, that's very nice. And you talked about your oncometer.
Oncometer.
Uh,
Yes, ma'am.
Oncometer. So you have, your team has developed the whole oncometer, or you have taken the idea from others, and then you have worked
No,
on
ma'am.
it.
It is the novel word and novel concept that has been developed by my honorable guide, Dr. Priyanjan sir and Dr. Rajiv sir, and they suggested to develop, I mean, whichever algorithms, not just in cervical cancer. I was fortunate enough to work under Dr. Priyanjan sir and Rajiv sir and Arpit sir. So we developed algorithms not just for cervical cancer screening, but also for ECG based screening, for other chest ray screening, because in medical world, any diagnosis, I mean, if I talk in modern days, ultra modern days, or most of the diagnoses are based on the image based data, like in terms of ECG, whether it's ultrasonography, whether it's CT scan, whether it's any other like MRI. So all these are image based reports that are taken
Right.
into
Yes.
consideration by the clinicians. So if we are able to develop a kind of algorithms that not 100% but at least matches up to 80 to 90% as per the parameters or the conditions which is taken into consideration by the clinician, then at least we can classify or lower the burden of clinicians on which you need to focus.
Yes. Yeah. That means only you are identifying yes or
Yes.
no.
Yes, ma'am. That is only for identifying and classification from normal to abnormal.
Okay, okay. And yesterday, Priyaranjan was talking about that he is trying, his team is trying to again find, in between your yes and no.
Yes, ma'am.
After 26 point something,
Yes, ma'am.
the normal,
Yes, ma'am.
and then the abnormality,
Yes, ma'am.
how severe it is,
Yes, ma'am.
whether
Yes, ma'am.
very severe, and
Yes, ma'am.
that part probably you people
Yes,
are
ma'am.
taking up right now.
Yes, ma'am. Yes, ma'am. Yes, ma'am. Yes, ma'am.
Are you work?
So,
Oh,
yes,
okay.
ma'am. Yes, ma'am.
And a colposcopy.
Yes, ma'am.
You said, okay. Before coming to that, I would like to know this ohm meter is now it's a software or hardware.
Ma'am, OM is a
I mean,
software. For
it's
hardware, as I told you, the
completely
colposcope is used. Yes, ma'am.
okay, okay. And colposcopy that you people are using this one, which is developed by. Already it is developed by some other
Yes, it's
researchers.
a Israel-based company, ma'am, Mobile ODT.
Israel.
Yes, ma'am.
Okay. Is it available? I mean, it is available in
I mean,
hospital?
I forgot to mention these things. I mean, for this research work, I was awarded with senior research fellowship from Indian Council of Medical Research for the first phase.
Oh,
Then
nice.
we were funded by the Indian Council of Medical Research as a full ad hoc research grant of 70 lakhs rupees, and we were able to copyright and develop the algorithms, produce the results, and we are again trying to submit for the second phase so that we can, as I told you, we need more and more images, more and more versatile. And so India is a very vast geography, as I told you.
Right.
We initially we acquired the cervix images, I mean cervigrams, from international databases, so the orientation of the cervix were different in comparison to the Indian cervix, I mean Indian women's cervix. And in India itself, if we compare the images that we acquired from the northeast women and the images that are present in the Delhi regions women, the parameters changes. So we need to develop or customize our algorithms based on the features on the geographical areas as well. So whenever the images or in real world the images are taken into considerations, or any type of women, you just need to fill these category and upload the cervigrams, and the result will be automatically generated based on your parameters. So the idea is very simple and crisp, ma'am.
Okay. So this is, I mean, the whole thing has been solved using EMD.
No, ma'am. EMD is a part of the oncometer. EMD has been
EMD, I
used.
mean, you are fine. You are class. EMD is doing one kind of like
Yes,
your.
ma'am. Yes, ma'am. Yeah. But for perceptual similarity, we have used EMD. Yes, ma'am.
Okay. And after that, what you are using?
When the results is generated, we kind of color code it, as I told you, for the clinicians to segregate normal areas and abnormal areas, see the
Okay.
level of
That
progression.
part. Okay. And this classification thing, through this, you are applying this oncometer.
Yes, ma'am. Yes, ma'am. So the results that is
So,
generated using the algorithm, ma'am, is ported on the
okay. That means
concrete
you are not
range.
using any, you are not using any other machine learning or deep learning
Now,
techniques.
for initial sets of for initial, I mean for pre-processing matrix calculations, we are using some basics machine learning techniques like matrix calculations, like hue saturations and others. But for final calculation and final perceptual similarity, because see, ma'am, as you know, there are some limitations as well in case of deep learning. Many a times when you do analysis on the same data sets, it
Right.
produces different results. And in case of cervical cancer screening, we could not take the risk that if I do the same image, input the same images
Yes.
for the 100 times, the result may be different.
Yes.
So in this case, 1,000 times you input the image, the result will be same. The EMD will be same. So that's why we use this algorithm.
So it's really it's a very good presentation, and you have done a very nice work.
Thank you so much, ma'am.
So Saurav, now you offer the thanks.
Okay, ma'am. So I'd like to appreciate the Dr. Shrivastav and Dr. Muthu Kumar for your valuable time and sharing your knowledge with experience to our participants. So on behalf of all the participants and on behalf of the organizing committee, I offer my sincere gratitude and thanks to both the resource person for this session. Thank you, sir. And there is an announcement for the participants. I have already shared. We have already shared the feedback form, this current session, and the MCQ test link also in the chat box. Please go through it, and we have shared it in the WhatsApp group also. So kindly submit the same by tonight 10 p.m. Thank you, and that's